Okay, so I'm going to talk about particle acceleration, in particular in a multi-island reconnection. And I'm going to talk about two specific types of systems. First one is the multi-island acceleration problem in anti-parallel field case, and then I'm going to talk about the case with a guide field. So, so there are some really extraordinary observations, I would say, that has sort of driven me towards addressing this particle acceleration problem. So just to remind you, in flares you get electrons, still on, up to MeVs and ions up to GeVs. And there's this remarkable statement back in 1976 that a significant fraction of the released magnetic energy appears in energetic particles. And that means very energetic particles. And this has really stood up to the test of time. And that means there's a remarkable efficiency of conversion of magnetic energy into energetic particles. And there's this paper that Sam Crocker just published, which I think is extremely important, and that is they've demonstrated that in a very high in the corona, the energetic electron component can reach beta unity. And that's in a system in which nominally beta is extremely small. So this tells you something very profound, I think, about the process. The other interesting thing is that there's been demonstrated to be a very nice correlation between the energy gain of the electrons and ions, implying that possibly there's a common acceleration mechanism for both. And then the other issue, which we've been working on recently, is the issue of anomalous cosmic rays, which are seen throughout the heliosphere, and I'll tell you what these are in a bit. But basically, they're up to 100 MeV per nucleon. And the question then is it possible that, in fact, that reconnection of the sectored heliospheric field could be a driver for these? And this is a much easier problem than I think the flare problem. So I'm going to start off talking about this problem, because this involves anti-parallel fields. So anomalous cosmic rays. So here's sort of what they look like, energy, and this is from the Voyager 2 and Voyager 1 spacecraft. They're heading out to the outer heliosphere, and so here's in 1987, here's the ACR spectrum, and here's the galactic cosmic rays. So, and here's 100 MeV. So this is 100 MeV for nucleon particles. The classical picture of ACRs is this. You've got the local interstellar medium, and there's a neutral gas coming in, and the neutrals come all the way into the inner heliosphere, and they get ionized and picked up by the solar wind that carries them back out to the termination shock. And the claim was that the ACRs were produced by acceleration of the pickup ions at the termination shock. Now, if you don't know about pickup particles, if you've got a neutral coming in here, it's coming very slowly, relatively speaking. Solar wind is coming in at 400 kilometers per second. And when that particle gets ionized, it gains a thermal energy of around the solar wind velocity. So these have relatively high energies, about a kilovolt or so per nucleon when they're carried out. So they actually dominate the pressure in the solar wind when you get out to these outer regions. Okay, so the big surprise was when the Voyager spacecraft crossed the termination shock. This is probably the easiest thing to understand here. That was in 2005. And they expected to see a peak in the anomalous cosmic rays. So here is showing 12 to 22 MeV per nucleon. And you notice that after it crossed the termination shock, the number of particles is actually going up and continues to go up for a long time. And that tells immediately that the local termination shock is not the source of these particles. Okay, so we have tried to put together a reconnection model for the ACRs. In particular, what happens is that the heliosphere develops a sector structure due to the fact that the magnetic field in the sun is tilted with respect to the rotation axis. So you get this flopping going on. And what happens is that so I'm going to show you a picture of what this looks like. But the point is that the current sheet that you get due to Parker's spiral magnetic field in the heliosphere is rather thick. And so it's typically stable to collisionless reconnection. You need to squish it down a lot until you can get the onset of collisionless reconnection. And so the result is that the sector structure survives all the way till you get out to the outer heliosphere. And then what happens is you go across a termination shock that compresses the sheets, and then furthermore those sectors are carried out towards the heliopause where they keep compressing more and more until our argument is that you will reach the point where you can have the onset of collisionless reconnection. And all of that energy will be dissipated. And so let me just remind you that here's the sun. It has a dipole field. So in that dipole field, as the sun rotates, gets twisted around, and there's a current sheet called the heliosphere current sheet. And the point is that there's the magnetic axis is different from the rotation axis, and so you get a sector structure. So here, this is an MHD simulation showing the toroidal magnetic field above and below, and you can see this very broad sector structure. This is the termination shock right here, so you get a compression of the sectors across the shock. And then, of course, as you get closer and closer to the heliopause, this is the boundary between the heliospheric solar wind plasma and the interstellar medium. Basically, your MHD simulation always runs out of resolution. But does anybody doubt that reconnection should happen here? I mean, this is an extraordinary MHD simulation, required really a lot of resolution. And so all of this magnetic energy in here really should be annihilated. Okay.
I could say how big is the ion mesh on the scale of that simulation?
Yes. So here's our argument here, and that is that what really counts for us is the current layer. And the current layer is about 100 C over mega pi in here. And then, of course, it can compress, and it should really further compress all the way until you get to the heliopause. And so, yeah, so it's about 100 C over mega pi in the inner heliosphere.
Jim, I missed something here. Why is an MHD simulation appropriate here? Are these collisional plasmas?
Oh, these are collisionless plasmas.
They're
Collisionless. This whole region here is completely collisionless. Well,
why does MHD
you do what you can, you know.
Oh, okay.
But you know, I have to say I was really impressed. I mean, Merav Ofer, who is the co-author on this work here, I mean, she did a pretty good job. But you know, this is, in my mind, a very impressive simulation. It's a very compelling picture.
How certain are we that the Voyager spacecraft are still returning good data?
Well, I'm going to show you some data from them. So, unraveling the magnetic field is actually very difficult. The Voyager spacecraft was not designed to measure the weak magnetic fields that they're seeing in the outer heliosphere. And they have to, maybe Jonathan knows more than me, but they have to continually adjust their normalization on the magnetic field. So it's a complicated process to unravel the data they actually have. But they believe that it's real, and it looks, you know, so what I'm showing here is the strength of the magnetic field as a function of time. This is the termination shock here. And this angle gives you the sector structure. It's the angle that the magnetic field makes with respect to the radial direction. And so you can see it keeps flipping by 180 degrees as you go through here. The sector structure is much rattier than in the MHD simulation. But still, the sector structure survives all the way out to the termination shock. So the picture here is not quite right because they couldn't quite get all the way out here, but the sector structure, the Voyagers are both within the sectored magnetic field region. Okay, so what we did was, what we're studying is a two-dimensional problem, and it's in this plane here. So as a function of radial distance, we've got reversed magnetic fields, and then the magnetic field is dominantly pointing in and out of the plane. So we're looking at that plane. And like I said, it's a simpler problem because basically it's nearly reversed magnetic fields. So we start off with a 2D simulation of 400 and something ion skin depths by a couple of hundred with a set of periodic current layers. The separation of the current layers is not as large as in the real system. This is like 25 C over omega pi, and in reality it's much larger than that. But we believe that the current layers in the real system should squish down until you get the onset of collisionless reconnection. So we see islands growing on individual current layers, then islands merge together until you get, these are not looking too good, but islands merging with each other throughout, and you get dissipation of almost all the magnetic energy.
What equations are you solving?
This is a full PIC model, similar to what Bill was talking about. So here's the movie of the time behavior, islands growing on layers, and then you see islands merging, and then merging across, so all these current layers. So the reason I like this problem is because you have a true multi-island system without having to go to 3D. And yet it corresponds to a quasi-real system.
Excuse me, Jim.
Yeah.
So, we were just saying that the squishing down process is something that's happening gradually.
Yes. Yeah.
Is it the right way to think about it that suddenly nothing happens until suddenly the layers become really thin and then blam, all the reconnection happens? Or
Okay.
do you more expect the reconnection to start happening as the layers narrow and you end up with something that's really very kind of stochastic looking at the time it gets down to that?
Yeah, I think that's probably right. So one of the issues is how do you get onset? And the second thing is, it's pretty clear to me if you get close enough to the heliopause, you're bound to get reconnection because they've seen enormous squishing factors in the case of the Earth's magnetosphere. So it's going to squish down. So one question is, if you have magnetic reconnection robustly going near the heliopause, how will it percolate back upstream? Because after all, you've got a bunch of islands forming there. They're going to produce perturbations to go upstream. Furthermore, downstream of the termination shock, you're going to have mirror instabilities. Downstream of shocks, you typically have mirror instabilities, which produce large magnetic perturbations. Are those perturbations large enough to squish current layers and therefore trigger reconnection onset, just like Bill was talking about in the case of collisional reconnection and secondary island formation? And of course, we really don't know the answer. So probably it's not just sudden fast onset.
Right, but it's
Yeah.
still of interest
Yeah.
to do this.
Yeah, it's still of interest. So, and we're learning a lot. My goal here was to learn a lot about island formation, how you get acceleration in islands.
Jim, sorry, question about this previous simulation. So if you run it long enough, do they all eventually merge into one island?
In principle, yes, but in practice, no, and I'll try to explain why. Yeah.
And another question, you say most of the energy is dissipated
Into,
or particle, so it goes into eternal energy.
I'm going to show you. Okay, I'll show you. So one thing that's important, and I'm going to argue is very important, is anisotropy. And that's discussed here on this set of slides 3 different times. and in particular beta parallel and beta perp. This is a little different than typically used in the solar wind plots, but anyhow, this is the fire hose condition, and here's the mirror condition. And so as time develops,
Multiple dots or the
every grid point in our simulation.
grid points, there's lots of particles on every dot.
Yes, many particles in each dot. So you can see that early in time, you get violation of mirror, and as time passes, you get this is now where reconnection is the most robust. You get violation of both mirror and fire hose. But then at late time, you can see what happens. The plasma really pulls back to these boundaries.
This is electron or ion?
This is total. I haven't actually done it for the two separately, but they're both contributing. There seems to be little doubt about that. So at the end, you definitely get instability, which is bringing the plasma back into within these boundaries. So it bumps basically up against the mirror and fire hose, and that means a very important self-consistency process in reconnection and island dynamics are the mirror and fire hose stability criteria. You have to take that into account. So this is just an example. Probably a lot of people have seen this. This is from the solar wind. This is from Stuart Bale's paper. And so here's the fire hose, and here's the mirror condition. And this is, I think this one here is delta B over B, indicating that as you approach these limits, you get fluctuations which are preventing the plasma from really significantly going across these boundaries. So we basically find something very similar. Now here's a very interesting result, and that is that, so the black regions are where you're violating fire hose, although not by much at late time, and this is where you're violating mirror. And you see, within magnetic islands, you basically bump up against the fire hose condition. All these magnetic islands, you're violating the fire hose condition on the inside, and then along separatrices, you're violating the mirror mode condition. Okay, so why is this important for reconnection? It's important because if you're at the fire hose marginal stability limit, magnetic field lines have no tension. You can write down the dispersion relation for alphane waves in an anisotropic system, and the fire hose condition is when this is 0. So magnetic fields lose their springiness at the marginal fire hose condition. And that means that the reconnection drive is gone, because normally if you have an elongated island like this, it would immediately try to shrink down. Tension. But there is no tension in this field line. Look at it. It's all at the fire hose condition. So at late time here, so you asked about whether it all goes to one big island. But reconnection becomes extremely weak at late time. And the fact that you even see stuff like this already tells you that the usual process is really not going on very well. And you see other things too, like this. Look at this thing. These things at late time normally would not exist. So the fire hose condition is a key thing. And then for energetic particles, so here's a simulation which we started with normal initial temperature for ions and electrons, and you can see the energy. You get a lot of high energy particles picking up. This is a case where we seeded in these pickup particles that we think are the source of the anomalous cosmic rays. And so one important thing to get out of this is that if you look especially at this, notice that this is much higher energy than these guys down here. You notice that the higher energy particles gain more energy than the lower energy particles. And this is typical for a Fermi-like process. The rate of energy gain is proportional to energy. So from this data alone, you might suspect that there's some sort of Fermi-like process. And then so we looked at where our most energetic particles are. And so here's the out-of-plane current, and the black crosses are our most energetic particles. And you can see they're clustered around here, say here, and here. And this is right where two islands are coming together. Here, here, and up here, this guy just merged. And then we looked a lot of test particles to see what they're doing. And, oh, I guess I didn't plot it in this spot. Oh. Okay. I got the wrong figure in here. But this guy here, for example, bounces back and forth. There were two merging islands here. And what you can show is as a function, you can plot its energy as a function of position. And it bounces back and forth and ramps up, straight up in energy. Every time it undergoes a reflection here, it gets energy. And the process is basically, you have an island here, which the ends are moving in at the Alfvén speed, and the ion is bouncing back and forth, and every time it reflects, it gains energy in a first-order Fermi process. So you can calculate the rate of energy gain, and it looks like this. And we've seen that with all these test particle simulations. Okay, so how do particles get accelerated in a contracting island? This is an important question. Forget about the reconnection process. Just assume you have a contracting island. Can we understand how particles get accelerated? And the interesting thing about it is, to lowest order in reconnection, you have area preservation. So it's to lowest order incompressible. So the green area, as it contracts, of course, as it contracts, it releases magnetic energy, but still, area is nearly preserved, and the magnetic field line length decreases. And then if you're familiar with the equation that a lot of astrophysicists use for calculating energy gain, which is called the Parker's equation, so F is an omnidirectional distribution function, and U are as convective velocities. You see that so these are just convection and diffusion. And the only energy drive term is proportional to divergence of U. So according to the Parker equation, you only get energy gain if you have compression going on right here. And then, of course, this equation was the motivator for all the shock, well, not all the shock, much of the shock theory and the breakthroughs they got in terms of predicting diffusive shock acceleration. It all came from the Parker equation. And so, according to this equation, there is no energy gain as you go from here to here in reconnection.
Help those of us out who don't know about the Parker's equation.
Yeah.
Is
U is a convective velocity of the
but
fluid.
it's spatial only? Space and time?
Yeah, space and time.
And
F is a distribution function.
but it's
So
not
U is
spatial.
specified. U is specified. You have a system with a specified flow field. And then you calculate the energy gain by calculating F, which is a function of V and T. Omnidirectional V and T.
How do you get this?
Kappa is a diffusion coefficient.
Is this just a phenomenological equation?
No, Parker derived it.
From what? Is it derived from a Planck equation?
Yeah, it's basically a Fokker-Planck equation. A lot of people have derived this subsequently, but really, this is really one of the fundamental equations for shock acceleration theory. I mean, people are still, in the heliosphere, people are still using this thing to calculate the distribution of ACRs in the heliosphere. It all came from the shock. That's why they thought it was the termination shock. It came right from here. Okay, but now the first thing what happened was we tried to publish some papers, and our astrophysics colleagues say, well, it's inconsistent with Parker's equation. There's no energy gain.
If this was derived, it was derived with a lot of assumptions.
Yes. Now.
F is a function
Yes.
of V, but there's no V dot grad F here.
V dot grad F. You mean like the little v dot grad F? Yes.
I think this is actually isotropy and high flow, right? And then you over each over the atoms, that's wrong.
It's a strong scattering model. Okay, so that's the fundamental assumption, is strong scattering. So the particles are assumed to pitch angle scatter very quickly. And the result of that is that the fluid is carried about by the convective velocity. you can have a diffusion process so that the v dot del term turns into a diffusion process. You see what I mean? Yeah. Oh, you've worked on this. Anyhow, so this is valid for an isotropic plasma, but so now I want to show you the resolution of the problem. So now let's go back and look at the Fermi process, or the island contraction process. So there's a number of conservation laws. First of all, the area is preserved, L times W. L is the length. And magnetic flux is preserved, B times W, between here and here. And then you've got, so here's the magnetic field energy from some initial state. And you can see as L gets smaller, L meaning the length here, then B goes down. And then you've got particle conservation laws, the magnetic moment, V perp squared over B, and then the parallel action. Well, if you put these two together, then you can calculate the energy gain of the plasma. So here's from the perpendicular P perp, and here's from P parallel. Now, you can see right away that as L gets smaller, V parallel gets larger. But as B gets smaller, V perp gets smaller. So P perp is going down and P parallel is going up. Okay, so that's seen here. So this is P perp and that's P parallel. So P perp goes down as L gets smaller, but P parallel goes up. If you do a linear perturbation analysis with respect to L, these two exactly cancel. In other words, if you start off with an isotropic plasma, which I've written this for, and you do a perturbation with respect to L, you get a -2 from down here, so 2/3 subtracts, cancels. In an isotropic plasma, if you start to go from here to here in an isotropic plasma, there is no particle energy gain. And that's consistent with the Parker equation. Parker equation says in an isotropic plasma, you start to squish, there is no energy gain. Yeah.
But isn't that then a problem with energy conservation? Because the magnetic energy is changing,
Yes.
but it has nowhere to go.
Oh, no, it goes into the convective flow. Okay, so I'm ignoring the convective flow because I'm interested in particle
So
acceleration.
that's another equation for the convective.
Yeah, the convective flow just, so what you do is you just add these two up and the rest goes into the convective flow. Yeah, and that's the alphanic flow inwards, fluid flow. Okay, but if you start off with an isotropic plasma, let it start to squish, pretty soon L gets much, so in other words, you have a finite contraction. This beats out this in the end. And so, so this is, Parker's equation is only valid during the initial stage in which you have the initial contraction. But if you have a finite contraction, the P parallel wins out over P perp. And that's why we hit fire hose on the inside of the islands. In particular, I'm going to argue then that this is a calculation in which you link the magnetic energy released with the particle energy gain. And of course, this is one of the, I think, very important observations in solar physics. And so what happens is the island contraction will continue until you hit the marginal fire hose condition. At that point, the rate of energy gain, in fact, plus the rate of particle energy gain is exactly 0. In other words, all the magnetic energy release goes into particles. And that tells you that in a reconnecting system, you should expect a large fraction of the magnetic energy to go into these energetic particles. Because at the marginal fire hose condition, that's exactly what's going on. And that tells you something else too, and that is if your initial beta, the energy gain, the magnetic energy that's released, then is going to depend on beta. Because if you have a low beta system, you can contract a long way before you hit the marginal fire hose condition. And you basically release all of your magnetic energy when you have an island contraction. But imagine in a high beta system, you've got an island, a stretched island, say, in a high beta system, and then you try to contract it, you're very quickly going to hit the marginal fire hose condition. And so the magnetic energy is proportional released, then becomes very small because in proportional to 1 over the square root of beta. So basically in a high beta system, it's very hard to get magnetic energy release from reconnection. And it's not just because there's not much magnetic field energy, it's simply because you hit the fire hose condition. So I have a student working on this, and this picture seems pretty clear, but it seems to be trickier actually.
What happens? Does the system just evolve but slowly, or just stay?
Well, it's like what I showed you earlier with these elongated islands.
So they just staying, or?
So my student has been doing this. He starts off with a very high beta system, and you don't get normal islands like Bill was showing.
Right.
You get these weird long islands that are like,
Yeah.
hundreds of C over omega pi long.
Supported by fire flow.
Well, then they evolve and you hit fire hose. But for whatever reason, you still get energy release, and we're trying to understand this because you almost get no electron acceleration, but you still get some ion acceleration. So we don't understand it. But it's very different than the low beta case. There's some issues. So anyhow, let me just say we put together a Parker-like equation in a one-dimensional model in which so this is the contraction, this is the rate of energy gain, and you have to modify it by the fire hose, a mock-up of the fire hose condition, and you get a one-dimensional equation in which you have a loss process and an energy gain process, and then you get power loss solutions, which it turns out you can solve for the power law, and let me just say that it matches the Voyager data with no fudge factors at all. So we pretty much match the Voyager data in this model. So that's what I wanted to say about this anti-parallel case and the ACR problem. And so, and then I wanted to go on to the case of guide field, which turns out more complicated, as you might expect. Okay, so first there are all these beautiful observations from RESI. This is the so in the middle of a flare, this was a gamma ray flare. The flux of photons versus energy looks like this, and then they model this photons as energetic electrons hitting the chromosphere, and you can back out the particle distribution function, and you get things that look like this. They often have a double power law with slopes, which this is one of the most intense flares. Typically, the power law is 3.5 to 4, but this one is a very intense event, so this is a very hard spectrum. Here, so here's the electrons up to start approaching an MEV.
This is X-rays on the photosphere?
This is X-rays from the photosphere. Yes. And then here's this remarkable Krucker paper that I was referring to before. It's very hard for the RESI satellite to see high up in the atmosphere because the instrument is overwhelmed by the energetic particles hitting the photosphere. But there's these so-called over-the-limb events in which they look at an angle and the limb of the sun blocks the foot points. And therefore, they can look up and see what's going on up above. And so he has these observations of emission from 30 to 50 keV and also radio emission. And so all this was from 2007 flare. And the claim is that all of the electrons in the electron in this region up here are the energetic component. There is no more background electrons. All the electrons lie between 10 kilovolt and several MeVs. And also the claim is that the pressure of these energetic particles approaches the magnetic pressure. So amazing result, really. So here's this correlation between greater than 300 keV X-rays, namely the electrons, and the 2.23 MeV neutron capture line, which is greater than 30 MeV protons. Very nice linear correlation, which suggests that the electrons and ions have a similar acceleration mechanism. Okay, so in the solar literature, there's lots of results that are calculating the particle energy gain from parallel electric fields. And so, on the other hand, our view was that the parallel inductive electric fields produced during reconnection are rather localized near the X-line. Furthermore, the X-line itself is not where magnetic energy is released. Magnetic energy is released as a magnetic field line downstream from the X-line, stretches out, relaxes its tension. That's where the magnetic energy release takes place. Yet magnetic energy release does not take place at the X-line. The X-line is required to break the field lines, but it's not where energy dissipation, no, I shouldn't say that. Energy dissipation takes place there, but that's not where the most of the magnetic energy is released. And so why would you expect this parallel reconnection electric field at this location, which is necessary to break field lines? Why would you expect that to be the source of energetic particles? Because that's not where the energy is. Okay, so our argument is that the single X-line model cannot explain, number one, the large numbers of energetic electrons. They see a very large number of energetic electrons. It's hard, you cannot filter them through the X-line. The X-line is too small a region. Furthermore, if you imagine that this E-parallel region was extended in space and particles come in and they get accelerated and stream down towards the chromosphere in this massive current, that current would produce magnetic fields which are many, many, many orders of magnitude greater than any magnetic field in the corona. So it's simply not sustainable to have a model in which you have electrons being accelerated along a separatrix region down to the chromosphere. It just doesn't work. Okay, so on the other hand, as Bill nicely showed in his talk, here's a guide field case of a guide field of 2. And even if you try to produce a single X-line, which we did by putting in a single X-line perturbation, it ultimately forms secondary islands. And those islands grow, those islands grow up and they convect downstream. They head downstream, but they're pretty big. And then they reform again. And I want to show you, we were discussing earlier in Bill's talk, how do these secondary islands form? So I want to make a brief comment about that. And I'll have more to say about this perhaps on, yes. I don't know if you saw what was going on there, but we're thinking now, what I'm going to talk about on Wednesday is that there's this very strong shear flow instability of electrons. It's a pure electron shear flow instability. Barrett actually had done some work on this a few years ago. And I don't know how well you can see this, but you can almost see, in fact, this vortex roll forming here on the out-of-plane current, which is what you see here. And we believe, in fact, that this is what seeds the magnetic islands. It's this electron type shear flow instability which seeds magnetic islands, and then they just keep growing. There's also data from the sun which suggests, so our argument is, from a theoretical point of view, in a sheared magnetic field, you don't expect single X-line behavior. You expect multiple island behavior. There's evidence from the sun of this also. So here's one example from TRACE. There's an X-line which they believe is up here, and you can see, I don't know if you can see all this. No, we missed it. I don't know if you can see very well. This is not coming out too well, but you see all this stuff coming down? People believe those are islands, structures coming down from higher up in this X-line region. Furthermore, if you look at the X-ray data, they see bursts of energy coming down on the 10 millisecond time scale. Bursty 10 millisecond energetic electrons coming down. Also suggesting that the acceleration process is a fine scale process and not a simple, huge, gigantic X line. Okay, so Bill showed this. So we believe that you'll get volume filling magnetic islands, and you want to study particle acceleration in the context of volume filling interacting magnetic islands. So let's see. If you look at the energy gain of particles that are undergoing reflection in islands like we discussed before, it looks like this. And you notice the alphane speed is the alphane speed. So for particles, the rate of energy gain is independent of mass. So electrons and ions both gain energy, could in principle gain energy by this mechanism. For electrons, there's really no problem. They can bounce back and forth very quickly because they have such high thermal velocity. For ions, it's a different issue because beta is small in the corona, the ions are moving much more slowly than the alphane speed, so you need a seed heating mechanism to get them up to a sufficient energy so they can bounce. So that's an important issue, but otherwise both species can gain energy in this mechanism, and that's nice in a sense because of the data I showed you, that there seems to be a correlation between the energy gain of the ions and the electrons. So if you're going to try to explain the large number of electrons, you must have an island region so big in the corona. You can't have this island region to be tiny like this, otherwise you couldn't explain all these numbers of electrons. But with an island region like this, you can explain the number of energetic electrons that they see in the observations. Okay, so I have a couple of slides on the seed mechanism, but I think I'm going to skip that. So if anybody's interested in the seed mechanism, it's basically a pickup process. We think it's a pickup process. The ions come across here, they enter into this alphanic outflow, and they behave like pickup particles, so they get a thermal speed equal to the alphane speed. That's an interesting topic, but I think I'm going to skip that. And let's just go to, so here's the problem, and Bill laid it out very nicely, and that is what you'd really like to do is study, multi-island reconnection in the case of a guide field. You really want to study a 3D problem. You have to do that so you get islands at different tilt angles, but that's certainly impossible for us to do, at least in the near term. If you want to get enough separation of scales, you'd really like to get separation of scales of the islands to your system size. So after we finished this ACR problem, which I described, we just thought, well, heck, why don't we do a similar system but with a guide field? And even though it's not a true representation of what's going on in the solar corona, it's a model in which you can learn about particle acceleration. So I think it's a reasonable test bed, although there's clearly some differences. The magnetic field line is not stochastic in a two-dimensional system, so it's not going to be exactly the same, but we can hopefully learn something. So we started looking at a multi-current layer system with a guide field, in this case of 1, putting in an extremely low beta initially. So this system here is identical to the one I showed earlier for the anti-parallel case. And I want you to look at the differences, especially at late time. And there's a really huge difference between what you get in this system and what I showed you previously. Keeping in mind that that was the identical box size. The only difference here is low beta and the guide field. And you look at late time on this thing versus before. It looks totally different. All these secondary islands are generated. You know, as reconnection proceeds, the X lines start breaking up, producing secondary islands. And so the number of islands you see here is a very large number, while in that other case you saw these big long things. So the process is really very different. Just the addition of the guide field changed everything. So secondary island formation, and we find is much stronger in the case of a strong guide field.
How strong is strong?
This is 1.
But this was also enough to stabilize all this fibers and...
No, 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 no,
Beta?
no, no.
Even at that low beta?
Yeah, well, okay, well, wait a minute. I'm going to show you. But this is the first point I wanted to make, and that is the behavior of the turbulence is fundamentally changed in the case of the guide field. Okay. Okay, so here's the same plot I did before. Here's our initial state. Here's beta. 1 is here, so it's initially very low beta. And basically everything is right here in this case. And then as time passes, you can see what happens. It starts going out, and it's starting to bump up against the marginal fire hose condition. It does not bump up against the mirror condition.
Do you have an even later?
We've run out of energy. We've basically taken all the magnetic energy, or most of it, and dumped it into the particles, and it's trying to get to this point, but it didn't quite get there. Now, I can redo a simulation in which I just sort of stick it up here a little bit, and then I think it will run into this, because there's you know, it's still going out here right towards this boundary.
Or you could just do a slightly higher beta, because these things will
Well,
switch
that's what I
together.
did. Slightly higher beta. Starting with a higher beta. Yeah, 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 right. Starting with a higher beta. But I'm pretty sure it's just going to bump up. I mean, you're already seeing a few points at the fire hose condition. So the guide field prevents perpendicular heating that we got before, so you don't. The weird thing is, I would have thought this would be more like the solar wind, but this plot doesn't look anything like the solar wind. So maybe the perpendicular ion heating in the solar wind is produced by something else. I have no idea. I'm not an expert on the solar wind.
So it prevents it because of what? Because of view conservation?
Yes, right. The particles, in that other case, the particles were heated when they crossed these current layers. And of course, it's known that electrons bounce around in there and the ions also bounce around in there. And this guide field of 1 is sufficient to suppress all that. Okay, and so now you know why I showed you the earlier plots first. Because this, oh, now you can't even see anything here. It looks much better on my screen. But anyhow, I'm plotting the sort of the fire hose condition here. Beta parallel minus beta perp minus 2. And you can't see very well. Maybe here. Tends to be bright along separator seas, and in a lot of the cores of islands, there tends to be a ring, which you might expect from Fermi type reflection. It's just the projector. Yeah. But anyhow, I guess what my statement is that I think that the fire hose condition is still the critical issue for reconnection and particle acceleration with a guide field. And as far as self-consistency, then, when you do test particle simulations in MHD fields, which is what a lot of people do, this fire hose condition is one of the crucial things that you have to take into account if you want to do the feedback problem. And then here's the particle energy gain from this guide field simulation. Now, there's something interesting here which we don't yet understand because this is relatively new. And that is, there's a huge difference between ions and electrons. The electrons gain energy very quickly, early in the simulation. And after that, they don't gain any more energy.
What's the mass ratio?
This is 100. Oh, no, 25. 25. They really, in late time, it's not exactly, it doesn't look like they're robustly getting heated anymore, while the ions, you notice, are continuing to ramp up in energy. And so why this is, I don't know. We still have to try to figure this out. But there's something very different happening between electrons and ions in this guide field case, which I don't really understand. The other thing here you might notice, remember I was discussing how much energy the ions gain with different energies. And you can see here, early in time, here, you know, all these ions are gaining pretty much the same energy, and that might be a property of the pickup process, while at later time, then you go back to this thing where the higher energy ions gain more, and maybe this is Fermi. But we don't really know yet. We haven't really explored this. So this is sort of ongoing.
It sort of looks like there's a limit or something that's being reached there.
You mean for electrons?
Both.
Well, we're running out of gas on the magnetic field. To get magnetic field energy has gone way down. It's you know, only maybe 15, 20% left. So that's really the reason these things saturate, is we're really running out of energy. That's pretty much it. Thank you.
Just very few questions, please. Unless you want to sacrifice a couple. Alex.
Well, I have a question, I suppose, to Chairman. So in Bill's simulation, what's the status of the finals of the Earth?
I don't know. I have not looked.
Will you?
Sure.
Will you look?
Yes.
Yeah.
Thank you. Next question.
But still, the other thing is, see, we've been forcing the system to generate multi-islands, and in your system, you've got islands forming, but then they go shooting out. So it's
Dimensional one, which is physical C of them.
yeah, it's certainly worth looking at.
So maybe
Yeah.
this week? Can you tell us on Thursday?
Maybe. I may be able to look this week. It doesn't fill it out.
If you could actually plot like this plot with the fire hose condition and the mirror condition, that would be at least the simplest thing to actually see where it might be going on that plot.
Yeah, so your heating mechanism depends on anisotropy.
Yes.
I looked at some magnetic data, and I never see anisotropy above 10 kilovolts. So
Mhm.
it's always isotropic.
Mhm.
So at least for the magnetic, I would not think you could get
Mhm.
this kind of heating there. But I don't know, is there any reason to believe that the magnetic moment is conserved at higher energies on the sun than in the magnetic?
But you have to look at the time scale over which the measurements are taken. So maybe Jonathan knows the time scale over which the measurements are taken.
I don't quite which time.
So for example, Jan, so imagine you've got an island there sitting there. Then our picture is that the island contracts over time, which is, say, the Alfvén speed over its length. And then during that contraction process, you generate local anisotropy. And then the particles get out of the island and they scatter. We know from the test particle simulations that when they get out of the island, they scatter. So that isotropizes the distribution function. And so there's a contraction, generation of anisotropy, then reisotropization. So it's a question of the time scale at which they're doing these particle measurements compared to the crossing time of magnetic islands. On a longer time scale, it should be isotropic.
Like the data I looked at is in the exhaust taken instantaneously.
Mhm.
Instantaneously, the exhaust.
In exhaust as opposed to an island, or?
Even inside islands, like the case probably Chen has looked at, inside
Mhm.
the island, the distributions are still isotropic.
Mhm. Okay, so I have to look at it.
Big islands, presumably.
Big enough for them
What
to
is-
tell.
Right.
See, my impression, so I talked to them about this, they claimed that they didn't have enough time to measure the anisotropy. So I'm a little surprised at what you're saying, because I quizzed Li Chen about this.
Like cluster is rotating, and once the magnetic field is in view, they take a snapshot of the distribution function.
Yeah.
But
So
how long is this snapshot? How long is
it's
it?
an eighth, 1/8 of a second.
Okay, is that enough?
That's right.
Should be enough, yeah. I mean, we've measured beam distributions. This work we did with Cindy Cattell on the electron holes. She was measuring beam distributions crossing when the satellite crossed separatrices, and the 1/8 was sufficient to actually measure the beam. But so are you? Oh, so you're talking about the energetic. You're not talking about the lower energy
Like
particles.
lower than you have anisotropy, but above 10 kilovolts with never.
Mhm.
I've never seen it.
Mhm. Okay.
Last question.
How large or small are the electrons generating kinds of energy particles in your,
How what?
how large
Okay, so you can see from that one picture I showed for the anti-parallel case. So this is one of our most energetic particles in the simulation. And so this was as big, clearly if the particle distribution is any bigger than this, then it's not going to be able to be accelerated. So this is sort of an upper limit. And then, of course, they go down much smaller.
And the scale case in iron fusion?
Right, yeah. Mhm. Yeah, mu is not well conserved in this. So all that nice picture I was trying to was the simplest limit. I think the most energetic particles are not going to have mu and J conservation very well satisfied. And clearly this guy here, which has such a big orbit that mu, it's hard to define P parallel, V parallel, and V perp, and maybe this is part of the point of so one should look at the size of the islands and the energy of the particles and see what their gyroradius is, because certainly in a particle like this, it's not going to be simple mu conservation. Yeah.
I had a related question. So
Yeah.
fire hose instability is supposed to be not close to the gyro radius, but not that far either. So
It's what? Say
are
again?
you sure you're actually resolving the most unstable fire hose modes?
Parallel road.
We're certainly resolving it because we're down to the Debye length here. Yeah, we're certainly resolving it. So, but those thresholds I drew were for the most simple fire hose and mirror stability conditions. They're the MHD version. So you can add other effects in and change the boundaries modestly. But I've looked at all these solar wind papers, and they're trying to do more exotic theories of the fire hose and mirror, but it doesn't, as a naive outside observer, it doesn't seem like they're changing all that much when you do that.